All right, good afternoon. My name is Sammy Vani, and the topic that my project was on is using genetic algorithms to tune a thrust vector controller's PID gains for an optimal landing. So the motivation for this project is thrust vector control, or TVC optimization, is starting to become highly desirable for launch vehicles and lunar landers alike. And if we can make this more efficient and consistent, that would have a big payoff for these spacecraft. And this is where I think genetic algorithms are an intriguing tool for this optimization problem because they scale very well with large search spaces. That certainly applies to phases of flight like a descent burn, where you have a lot going on to consider. Now, when I view this project kind of from a top level, I decomposed it down into kind of three main phases of work. And that includes first creating a sim environment from scratch to mimic the flight dynamics, then implementing a PID controller with fixed gains to really actually gimbal that main engine and get thrust vector control. Then actually tuning that controller to maximize the downrange distance and using a genetic algorithm to actually find what the best gains are to that end. Now, I will note that objective is a pivot from what I originally set out to do, which was basically have a fitness function that evaluates and tries to select for the best set of gains that allows for the rocket to have an upright landing. Part of that, though, is the sim has a limitation right now in applying discrete torques, which I'll kind of mention a little bit more in the next slide or two. So that's why I went with this objective, because the sim is capable of simulating this. So for some related work, also literature review, evolutionary algorithms and genetic algorithms have been around for a while, but really in the early 2000s and up until now in the past 20 years, they've started to flourish with just the widespread kind of computing capability, but also tool providers really packaging these friendly tools that start to become easier to apply to a wide variety of optimization applications. A good example is actually the distributed evolutionary algorithms for Python, which is DEAP. Um, it's one of, I feel like, kind of the two mainstream Python genetic algorithm tools, and that's the one I actually use in my project here. Now, in parallel, many folks, both in academia and in industry, have started to actually use genetic algorithms for serious PID controller tuning to accelerate their development, particularly as we've talked about already with large search spaces. And so some good examples that I've used as reference is some work that researchers in industry folks have done to tune autonomous hovercraft controllers, to actually tune controllers that are involved in the gearbox operations for automotive applications, and then as well as manufacturing droplet controllers. When it comes to spacecraft, as you might imagine, there are a variety of hybrid and custom control schemes that are actually applied, as well as a kind of a variety of ways that these are tuned. But I would say maybe more traditional methods that are actually have a lot more tests involved. But genetic algorithms have been applied sort of in the preliminary control design space, and that's where I think they could add a lot of value. So when I think about actually breaking down this problem, um, the first thing that I did was trying to capture the physics of a 2D trajectory. And so what I did is I have four primary ordinary differential equations that are driving the physics behind the simulation. And so what these give me is the velocity, the flight angle, which is the angle from the horizon to the nose of the rocket or the direction of flight, the height, and the downrange distance. Now, I will note, if you kind of study these equations a little bit more between the change of velocity and change of the flight angle, they're coupled together. They contain parts of each other. And so the consequence of that is it can be difficult to apply a pure torque to the vehicle, or for example, the spacecraft or the descent stage may be falling, but I could apply a moment to it where it still maintains its overall direction of flight, but the nose of the rocket maybe is changing. So essentially, I am missing probably an additional equation that can model the change in the angular velocity. And so that's something that I would track as forward work. Now, as part of the simulation as well, I am simulating the varying gravity and density that change as a function of height, as well as the varying propellant masses from the ascent stage, the descent stage, and the total mass in general as we release kind of a fictitious payload. Now, for the launch vehicle itself, I wanted to also simulate the phases of flight that are going on. So there are 5 total phases. There's 2 stages actually associated with ascent. One is just your initial ascent where you're burning that motor. And then the second is where you actually execute a gravity turn and you incline the rocket more towards the horizon to increase altitude by expelling less propellant. After you totally expel all the propellant from the first stage solid rocket motor, we go into a coast phase where the rocket is still gaining altitude. And then at the apex of that altitude, the payload and the first stage separate, and you're left with just a descent stage. So then we enter actually into our 5th stage, which is essentially uncontrolled free fall. And at some point, the thrust vector controller kicks in, and then that's where we have a kind of a controlled descent burn where our controller is actually operating. And then if propellant does run out of that second stage, a descent stage, then we'll go back into that uncontrolled free fall. When it comes to the controller itself, I am just having one single or main engine thrust vector control. And that engine, which is, say on the back of this rocket here, it does essentially have a 120-degree sweep, 60 degrees on each side of it. That is extremely generous, but that's in part because I have no additional effectors, no little attitude jets or anything that can impart moments. I am chasing a set point of 0 degrees, which essentially means pointing the nose of the rocket towards the horizon. And what I'm ultimately trying to select for is the best gains that maximize the downrange distance. And so I do that via the genetic algorithm. And I also run some experiments by changing the configuration of the algorithm itself to change the probability of mutation, which allows us to explore the search space more, as well as the probability of crossover, which still gives us the ability to kind of have reasonable convergence without waiting all day for it. So these are some results, kind of just from some arbitrary gains from the sim I created. Again, this is all Python and also just from scratch. So to give you an idea of what's going on, I have this phase plot. These integers correspond to the kind of enumerations I was talking about before. So this is our initial ascent. This is our ascent with a gravity turn. Then we go into a coast phase. And then immediately after coast, we're just in an uncontrolled free fall into our thrust vector control kicks in. So this is a controlled descent. And then we run out of propellant and we go back into uncontrolled free fall. So this is our height and downrange. This is essentially our x distance and our y height. And you can kind of get a feel for what's going on with the trajectory here. If we look at our velocity plot, just note this is in kilometers per second. This becomes much more clear where basically the first stage stops burning. So right after this, we go into coast. So we're still gaining altitude up until this peak here at about 70 kilometers, but we're falling and falling in velocity until the rocket turns over and we start falling back towards the Earth and the velocity picks back up. This plot is illustrative of what's going on with basically the rocket's angle relative to the horizon, as well as what the controller wants to do, and the error associated with what it's trying to command. So you can see this controller in particular is not very good, and you'll kind of see this on the next slide, but it way overcorrects. It actually pushes us away from where we want to be, and then tries to sling way back and overcorrects, and that will have a pretty bad impact on the trajectory. I will also point out that we're tracking the masses here. So as you might imagine, right, we burn out all that propellant in that first stage. That lines up right here where we see that velocity drop off. And then the second stage here is in orange. And so then we burn all that propellant, and that kind of lines up with this asymptote where TVC tries to stop commanding because we don't have any propellant to do anything at that point. And then we do have representative thrust here. So constant thrust for the first stage, and then basically about 20 times less than that thrust for the second stage. And just to illustrate, we are tracking the changing density and gravity as a function of height, which is associated with our trajectory. So that trajectory for those arbitrary gains looks a little bit like this, where we have that initial ascent, we turn over, the controller engages, but kind of just struggling in what it's supposed to be doing, and actually flips the wrong way, and then away tries to overcorrect, and we get this history right here where we actually double back on ourself. Um, and we don't want to do that, right? Our objective is to maximize the downrange distance. And so to that end, we can apply a genetic algorithm. We can train it for several generations, and we get the best gains, and that gives us a trajectory like this in the middle here, where we have the same ascent profile, except this time we turn over, TVC kicks in, we pitch up, and we're actually able to maintain a stable heading here on that 0-degree set point. You'll see it again right here. So we pitch up, and then we're still able to maintain that, and then we run out of propellant, and then we fall back down towards the Earth. So what actually happened here was we had 6 generations that each had 10 individuals associated with them. And this algorithm was configured where we had essentially a pretty healthy chance of individual mutation. So we could fully explore the search space and flesh out all the different essentially combinations of the proportional integral derivative gains. But also still have the ability where we can converge in a reasonable amount of time. And 6 generations is pretty good for a total of 60 participants. And what we found is we eventually get a maximized downrange distance of 207 kilometers, and that occurs from a pure proportional controller. Now, I will note this pure proportional controller is probably an artifact of the fact that we can't apply discrete torques realistically in the sim yet, which kind of leads us to this. Now, it's also interesting to look at the statistics from the generations. So all these numbers are downrange distance in kilometers. And so you'll note that as the generations proceed and we get to the last generation, we've actually basically selected totally for that maximal distance. I am rounding here, so there's a little small differences. But the algorithm has performed quite well for only 10 participants. So these are the simulation results for those optimal gains. So if you remember a few plots back what it looked like for arbitrary gains, you'll definitely notice the changes in these profiles here. So I'll specifically point out the velocity here. So this is our first stage burnout. We enter our coast phase, and then this kind of little section here is really where the engine is kicking in. And so we're leveling off before we fall back to Earth because we ran out of propellant in that second stage solid rocket motor. And then here, this is much more obvious, which is right when TVC gets the ability to kick in, we're going to bring that nose straight up to the horizon. That's the pitch angle. And we're actually going to hold it there. So we're right at our set point, which is awesome. And you can see this is the gimbal angle of what the main engine is doing. And it's just kicking back and forth between basically that 60 to 60 plus or minus 60 range it has. Now, I have no limits on how quickly essentially that servo could actuate. Obviously, in real life, we wouldn't be doing this. So that's something I would clean up in the future. But then at that point, we run out of propellant. So the nose of the rocket is going to drop. TVC is off. So the psi angle is just matching the theta angle. And of course, our error is building at that point. So we can look kind of generation over generation to get a feel for what the algorithm actually did. So we initially have something like that with those blue dots, if you saw them, where we kind of were randomly sampling across the space. And as the colors change, those are the subsequent generations. And what you'll notice is this clustering eventually of the lime green dots here in the bottom corner. And that's our last generation. And that's focused on basically a pure proportional controller. So this plot kind of really illustrates why genetic algorithms can start to shine. This is, just a 3-dimensional search space, but you can imagine in a very n-dimensional search space, just randomly trying to sample through and find your best gains or best parameters would be quite laborious. You'd burn a lot of cycles, but the genetic algorithm really allows you to navigate towards those hot spots. And that's how we found our best gains here. Another way to look at this is the plotting of the worst individuals from each generation. So I plotted the worst trajectories from each generation. And what you'll note, though, is even in the 6th generation, the worst trajectory is still very good. It's pushed our downrange distance out quite far, almost to our maximum value. I think it's maybe a kilometer or two below it. But you also know, because we configured a fairly high mutation probability, the fifth generation, it's still taking chances. So the worst performer from the fifth generation is this purple line, and that's only the third best line. So it's falling behind the worst performers of the fourth and third generation. And that's not necessarily a bad thing because we do want to make sure that we're fully exploring this sample space and basically not getting a false positive and narrowing in too quickly. Okay, so to kind of close this out with some discussion, as I've noted right now, the sim is limited by its ability to essentially apply a pure torque at moment. So with those limitations, we are led to a pure proportional controller maximizing the downrange distance. I will say though, this project's been very rewarding to kind of get in and from scratch implement some of the physics, as well as gain an appreciation for applying the controller and using a genetic algorithm to tune that controller. If I were to continue this project, some forward work I would have is first and foremost, introduce another ODE that can actually capture that change in angular velocity, which at that point I would be, considering the inertia characteristics of the rocket. And then I think, reasonably impact the flight angle to essentially land the rocket. And then I would also probably introduce some additional effectors, some attitude control jets that give me some more control authority. I would then rerun the experiments in which you saw, and then I would basically change the set point to 90 degrees, which would be landing the rocket upright. And instead of trying to maximize the downrange distance, I would change the fitness function to essentially a combination of at our final height and time, trying to make sure that we're closest to that 90-degree upright landing, as well as nulling that velocity. And then finally, I would consider expanding the genetic algorithm to make the search space larger, to optimize the trajectory further. So things like when we actually, at what height do we turn over for our gravity turn in the ascent stage? What some of the parameters of that second stage actually look like? At what time or at what delta height thrust vector control actually kicks on? These would be interesting parameters to include in the search space and overall try to see how it could impact our ability to land the rocket. So that's all I got. I want to thank you for the time and appreciated the semester. Thank you.